It's Paul here to teach you how to use row reduction to carry out some tests in linear algebra for linearly dependent and independent sets of vectors, to invert a matrix, or to find the image and kernel of a linear transformation. If I've used words or phrases that are not yet familiar to you, have a look at subsections 1.3, 1.4, and 1.5 of the executive summary, or better yet, watch Kate's preview video on those sections. I propose to do as little row reduction by hand as possible, so I'm going to load the practical math library so I can use the RREF function. And let's start out with our first test. We've got a set of vectors v1 through vn, and we want to test whether they are linearly dependent, which means that I can find a set of coefficients, not all of which are 0, so that by applying those coefficients to the individual vectors, I can make the 0 vector as a linear combination. Let's choose 4 rather arbitrary vectors, each with 3 components, and use them as the columns of a matrix. So there are 4 vectors bound together into a matrix. Previously, when we were solving linear equations, we called the unknowns x, y, z, and w. Now we're looking for unknowns a1, a2, a3, and a4. If we find a solution, then by applying a1 through a4 to these 4 columns, we will have made the 0 vector and shown explicitly that the vectors are linearly dependent. You may want to row reduce this by hand, but I sure don't. So I'll call RREF and interpret the result. What does the top row mean? It means that A1, the first unknown, plus 2 times A4, the second unknown, equals 0. And I can interpret the second and third row in similar ways. Remember now, in a situation like this, we have to choose arbitrarily the value of one of the unknowns. A particularly convenient choice is a4 equals -1. And once we choose a4 equals -1, we can calculate the other values, 2, 1, -2, respectively. And we found our solution. The solution vector A is 2, 1, -2, and -1. And what that means is that if I multiply the matrix capital A by this solution vector little a, I end up with the 0 vector. That shows that 2v1 plus v2 minus 2v3 minus v4 is equal to the 0 vector, and that's exactly how to prove that these 4 vectors are linearly dependent. Suppose we started with linearly independent vectors. Here are 4 4-component vectors, and I chose these carefully to make sure that they were going to turn out to be linearly independent. RREF is sometimes happy only if you slap an extra column of zeros on the right-hand side, and here you can think of this as the equals 0 on the equation that determines linear dependence versus linear independence. I row reduce this matrix, and you could read the answer directly off the row reduced matrix. A1 equals 0, A2 equals 0, A3 equals 0, A4 equals 0. The only way to take the original 4 vectors and form a linear combination that equals the 0 vector is to make all your coefficients be 0. That's exactly what it means to say that these 4 vectors are linearly independent. Now let's consider a more general case. We've got 6 3-component vectors. If I tried using the function in the practical math library on this 3 by 6 matrix, something goes wrong, so I had to row reduce by hand. But since I was willing to have R do this automatically, I'm not going to talk about this. I'm just going to run it through line by line, make the first column pivotal, make the third column pivotal, make the fifth column pivotal, and I am done. So this is this matrix row reduced to echelon form. Interpreting this now is interesting. So let's look at that first non-pivotal column, V2. What that means is that the second column of my original matrix is twice the first column of the original matrix. You can just see that at the top of the screen. You might already have noticed that 2, 4, 6 is precisely twice 1, 2, 3. What about column 4? Column 4 is non-pivotal. That means that the fourth vector can be written as a linear combination of the ones to its left. And in fact, it can be written as a linear combination of the two pivotal columns that emerged to its left. I can actually check that. It's being checked on line 58, where I show that V4 is the same thing as V1 plus 2V3. And finally, the sixth column is the last of the three non-pivotal columns. That tells us how to express column 6 in terms of columns 1, 3, and 5. Next topic, how do we invert a matrix by row reduction? I'm going to work in Z5 for the simple reason that ordinarily when I do row reduction with matrices of real numbers, fractions start showing up. R converts them to decimals, and it's kind of hard to visualize what's going on. In Z5, there are no fractions. And furthermore, I can write down any 3 by 3 matrix that I feel like, sure that the arithmetic will stay straightforward. The only thing I have to check is that I didn't accidentally pick a matrix whose determinant is equal to 0. Here the matrix that I wrote down has a determinant of 2, and we will be fine. Remember, in Z5, dividing by 2 is the same as multiplication by 3. The secret of doing matrix inversion is to append to your original square matrix the standard basis vectors. Here there are 3 of them, so I now have 3 rows and 6 columns, and I start row reducing. I have no function to row reduce in a finite field, so I have to do it by hand. The first thing I do with this extended matrix is I make the first column pivotal. What I'm doing is dividing by 2, but in fact that's equivalent to multiplication by 3. Subtracting off appropriate multiples of the first row from the other 2 rows gives me my first pivotal column. Dividing the second row by 2 gives me my second pivotal 1, and a little bit of subtraction makes the whole second column pivotal. Finally, dividing that 3 at the bottom of column 3 by 3 converts the third row to give me my third pivotal 1, and a bit of subtraction of the third row from the first and second rows gives me my third pivotal column. There's no way with 3 rows that I can get more than 3 pivotal columns, so the process of row reduction is done. The last 3 columns are now the inverse matrix. So we have successfully computed the inverse of the original matrix A. How do we check that? We extract using comma 4 colon 6 the last 3 columns, store it in a matrix A, I, and V, and check that when we multiply that by A, remembering to do the matrix multiplication modulo 5, we get the identity matrix. We've computed the inverse. This is the most efficient way of calculating the inverse of a 3 by 3 matrix, and for matrices bigger than 3 by 3, this is vastly more efficient than any techniques you may have heard about that involve the use of determinants. Now this next topic is of great theoretical importance. I want to show you how to verify that a given set of vectors fails to span Rn. And this is going to be our first theoretical use of the elementary matrices you learned about earlier. Remember what span means. If a set of vectors spans Rn, then any vector in Rn can be written as a linear combination of them, not necessarily uniquely. So here's a set of vectors that fails to span R3. You look at them and say, there's 4 of them. How can they fail to span a 3-dimensional vector space? And then you look a little bit harder and say, oh, I get it. The second one is twice the first one. It doesn't really add anything. And it must be that somehow the fourth one can be made out of the first and third ones. Well, we know how to discover this. We will convert these 4 vectors into a matrix. We're about to row reduce it, but it's very useful, even though we're not computing an inverse here, to slap on the identity matrix. So we've now got 7 columns in this matrix. Who cares how many columns we are faced with? We are using a computer to do the row reduction, so it's no more work with long rows than with short rows. Unfortunately, RREF doesn't work on this matrix, so I have to do it by hand. I'm not going to waste your time reading the individual steps. If you're still feeling shaky about row reduction, you might want to read this script on your own, but all I do is I make the first column pivotal. I look at the second column and see it's doomed to be non-pivotal. We already figured out that that was going to happen because the second vector was twice the first vector. But now something interesting happens. The second row starts with lots of zeros. The third column is going to be pivotal, but we want the pivotal one in the second position, so we swap the last 2 rows, and now we are in business. We complete the job of making the third column pivotal, and now interpret the result. Columns 1 and 3 are pivotal. That means that of the original 4 vectors, the first one and the third one are independent. And in fact, they are a basis for the subspace spanned by V1, V2, V3, and V4. That subspace is not all of R3, and sometimes we want to find a vector that in R3 that's not in the subspace, and it's not immediately obvious how to do that. Suppose we'd used elementary matrices. If we'd used elementary matrices, we'd keep multiplying them by the original matrix, and that's what that identity matrix was for. It has preserved the product of all these elementary matrices. So the last 3 columns is the matrix E that row reduces my original matrix. We can check that. If I apply it to the matrix B, it row reduces the original matrix. E matrix multiplied by B is in echelon form. But remember, the matrix E is a product of invertible elementary matrices, so the matrix E itself is guaranteed to be invertible. The solve function will tell us the inverse if we want. And now, finally, we can construct a vector that's guaranteed not to be in the image of B. All we have to do is apply E inverse to the last standard basis vector, C 0, 0, 1. And in this case, what we discover is that we get a vector that happens to equal the second standard basis vector. That means there is no way to write the second standard basis vector as a linear combination of our 4 vectors. We have found a vector that is outside the span. You might think that there's an easier way to do this, but there is not. This topic is discussed at great length in John and Barbara Hubbard's textbook, and you might also want to read about it there. Final topic. We start with the linear transformation represented by a matrix. Let's use the same matrix B, and we want to construct a basis for the image of B and the kernel of B. We've already done the row reduction, and there's the answer. finding a basis for the image is easy. Just look at the pivotal columns, V1 and V3. That tells us that the first and third of the original columns are linearly independent, and they form a basis for the image. What's harder is finding a basis for the kernel. This is discussed in detail in the textbook and also described in Kate's preview video. I'm going to show you how this algorithm works when you have a computer to help you out. I focus my attention on the non-pivotal columns, the second column and the fourth column, and I construct a pair of prototype basis vectors for the kernel that have basically the 2 by 2 identity matrix in the second and fourth positions. The first one has a 1 and a 0 in the position of the two non-pivotal columns. The second one has a 0 and a 1. The other two components, the first and third components, are unknown. We've got to figure those out, but we can figure them out by using the row-reduced matrix. So I apply the top row of my row-reduced matrix to my first kernel vector, and when I look at this, I see that the row-reduced matrix tells me that 1 times x1 plus 2 plus everything else is 0 equals 0, and therefore that x1 had better equal 2. Doing the same thing with the second row tells me that z1 is going to be equal to 0, and I never get more than one of the unknown quantities in these equations. So the first row tells me x1, the second row tells me z1. And there's my first basis vector for the kernel, the one that has a 1 in the second position, a 0 in the fourth position. Multiply b by this vector. Yes, indeed, it is in the kernel. There's the row-reduced matrix again. We need to look at it to go after the second one. This second basis vector for the kernel has a 0 in the position of the first of the non-pivotal columns, a 1 in the other position, and reading off what the two rows have to say about this immediately tells us the values of x2 and z2 and gives us our second basis vector for the kernel. There is a simple rule for doing this, but I don't use it because I can never remember whether it has a minus sign on it or not. But if you're good at memorizing, you can say, if you want a vector that's in the kernel that has a 1 in the position of non-pivotal column 2, just look at the two entries in column 2 of the row-reduced matrix and put them in the two empty slots. There's K1. And to make the second basis vector, which corresponds to non-pivotal column 4, all you have to do is slap a minus sign on the two entries in column 4, put them in the empty slot, and you've got your second basis vector for the kernel. We've now actually proved a rather profound theorem. From each pivotal column, we've managed to get a basis vector for the image. From each non-pivotal column, we've managed to get a basis vector for the kernel. But the total number of columns is just n, the dimension of the domain of the function represented by the matrix. And by our algorithm for constructing these bases, we've proved what's generally known as the rank nullity theorem, namely the dimension of the image plus the dimension of the kernel is equal to the dimension of the domain.